Today, as mentioned, is which streaking database should I use? This is a pretty vendor and particular technology agnostic sort of presentation. So we're basically going to go through the different types of NoSQL databases and what their main applications are. So this is who I am. I've been programming since I was like 8. I'm most known for founding a project called Poi, which was a port of Microsoft's file formats to Java. Before that, I was writing OS/2 device drivers. I joined a company called JBoss in 2002, which was sold to Red Hat in 2006, and that's roughly around when in 2008, I founded Open Software Integrators. A former board member and a current member of the Open Source Initiative. I also write a column in InfoWorld. It's the strategic developer column. Open Software Integrators, again, was founded November 2007, and we have offices both in Durham, North Carolina, and Chicago. And we started out mainly focusing on this Linux, Java, and virtualization, but now we have a lot more of a big data and NoSQL kind of tilt, as well as cloud. So we're going to go through why you wouldn't want to just use the relational database or an Rdbms for everything. We're going to talk a little bit about, gee, there's things that are operational versus analytical stores, and the type of database you use is not necessarily the same for both. It wasn't even the same table structure for relational databases. Then we're going to go through the different types of databases: key value, column family, document, graph. We'll talk a little bit about Hadoop, and then we'll talk about the convergence of clustered file systems and databases, and then we'll draw some conclusions. So the first thing in talking about this sort of a topic is, the first thing that comes up is, why don't we just use the Rdbms for everything? That's sort of been the way the industry has been doing it for the past several years. But why isn't that, why do I care about NoSQL or big data or whatever? Why don't I just keep using Oracle in particular, but a relational database for everything? And one of the goals I had for the article this presentation was based on, with the same name and this presentation, was to sort of handle the quote-unquote teddy bear in the room. So I don't know if you guys have seen this. It may not be safe for work depending on where you work, but it's a debate between somebody who said, hey, we just chose MySQL for our application, we're very happy, and then the bear on the right says, well, why did you do that when this particular NoSQL database has the web scale? It's the secret to the web scale sauce and what have you. And part of the problem is in the hype cycle, we lose sight of what are the reasons for this technology. A lot of this comes down to the CAP theorem, which says that we can only do 2 of these very well at a time. So we've got consistency, availability, and partition tolerance. And yes, we can handle all 3 in the same system. We just can't do more than 2 at the same time. So we can have consistency, availability at once. We can have consistency and partition tolerance, or partition tolerance, availability, whatever, but not all 3. And I would even throw in here sort of almost another one, another factor. It may not be part of the CAP theorem, which would be data complexity. So for a relational database, its CAP characteristics, it's great at consistency, it can be okay at availability, but it's not real good at partition tolerance. Yes, there are relational databases that support partitions, but if you look at the way that they do them or what they ask you to do, it's a lot of work. Another big issue is the process model. So when we use a relational database, in general, we end up with a single process model. Yes, you can use rack and you can have a couple instances or a few instances, but not that many instances on the whole. So a lot of what we're hitting is the single process model. So we've got, say in the case of Java, where we've got a connection pool and we've got threads, and this is not just Java, but a lot of technologies. I just picked two with different thread models. And then we have the standard PHP prefork, which does sub-processes. And so we get a database connection per request. In the Java, we don't necessarily have that. But then they all thrash at the relational database. So you end up with a lot of threads per process on PHP because it doesn't support connection pooling, fewer on Java. This becomes less of a problem if it's a big problem for your standard PHP, MySQL, LAMP stack kind of application. You go and you do a net stat and you see time weights out, out the gazoo, and you realize, gee, not connection pooling is a big problem. It becomes less of a problem with NoSQL databases or what have you, where we don't have a single process model, where we've got lots of additional processes handling that those connections. So that becomes less of a problem. Yes, we could reduce the problem with PHP, but we eventually have this, a similar problem with Java, in that as we scale out and we have more instances of Java, or name your favorite threaded runtime, we still end up with, gee, we've got too many connections going to too few of database servers. Some of the reason that things are the way that they are is the historical context under which relational databases took control. So originally, 10 megabyte disks in the Rdbms era, at the beginning of the Rdbms era, were big. Scalability meant more disks, controllers, and CPUs. You would balance your temp segment, your rollback segment, your redo logs, and all that on different disks and hopefully different controllers. We put the index for a table space on a different disk and hopefully controller and what have you. And we'd make a balancing act that was sort of based on economics and performance and sort of this vertical scalability. In the same time frame, CPUs went from 4.77 megahertz to 3.4 gigahertz. Disks went from 64 kps at a 70 millisecond seek to now we have disks coming out like the Fusion IO stuff that's 6 gigabit per second on the flash drive, and that's a huge jump. Network speeds went from under 4 megabit to gigabit to bonded gigabit and beyond. Just the other day, there's a article that IBM's actually managed to put fiber optics on chip directly and such that, when you look at, okay, we could potentially network directly off the motherboard from fiber optic, it gets pretty insane with the kind of speed increases that we've seen from what we were at. Disk speeds for a long time did not keep up with CPUs, so we had these massive CPUs speed increases. It was doubling, for a while it looked like we'd get twice as many megahertz to gigahertz, whatever, every year, and then it sort of bottlenecked out. Another big thing with relational databases, they're based on relational algebra, which is an extension of basic set theory in mathematics. And not every problem is just a set problem. When we have things like direct path, or which thing contains this other thing which has this other thing. So if we're looking at like derivatives in finance or what have you, where we've got fund to fund to fund, and we want to figure out what top level fund contains what bottom level fund, or we have your friend likes kittens, her friend likes puppies, so maybe you'd like to like puppies or kittens in the social networking kind of example. Writing that kind of code in a relational database is laborious. It can be done, but you have to do query on row 1, which leads to query on row 2, and what have you. So you end up with several queries and lots of lines of code to generate what's 2 lines of code with a different type of database. So sometimes relationships are as important as the data. Sometimes the data is even simpler than the relational model, but we have higher needs of availability and et cetera. In the end, one size really did not fit all. A lot of performance tuning and stuff like that that we've done for clients, scalability and performance tuning that we've done for clients, usually we get called in, okay, let's look at the garbage collector in Java, and then we're like, okay, it's not the garbage collector. It's almost definitely a database problem. We spend all this time figuring out, okay, it's just a database tuning kind of issue or what have you, or you just need more horsepower, more databases and what have you. When we talk about data complexity, or we talk about this NoSQL landscape, we have two sort of major factors, which is the size of the data, how much data do we have, and then the complexity of the data. And then we have, gee, what databases do that well? So this is a little deceptive in that I think relational databases keep a little bit more complicated data than say, a key value store. But a key value store handles large size data, but it's basically sort of a map interface. We get down to a graph database, and a graph database really can't handle the same data sizes as document or key value type data stores, but it handles way more complicated data or different types of data complexity than do relational document key value stores. So another sort of major driver behind this sort of NoSQL big data or polyglot database sort of movement is that the industry has what I like to call data-rhea, which is, it used to be you were capturing this tiny amount of data, and yeah, they never wanted to throw it away, but it wasn't, operational data was really important, but it wasn't so important past auditing or whatever your tax reporting and what have you, inventory shipping. Now we're capturing a lot more data about everything. And companies are really reluctant to throw that away, whether it be regulations, whether it be, a litigious society, whether it be that they're doing more with the data, or whether it be just they're scared to throw it away. We've got more data that we're keeping for longer. And some of this is just because storage has gotten a lot cheaper. And so, economics say, okay, when storage gets cheaper, whatever the demand for it generally goes up. So some of it's about that, and some of it's just different uses and more computing power and what have you. So we need a way to hold more data. We need systems that scale to hold more data. And we need systems that can handle more data at once. Meanwhile, while we were getting all this great demand built up because of all this system evolution, Moore's law ended. So Intel says it ended, that it ends next year in 2013. I kind of think it sort of ended for all intents and purposes, because at one time that meant, so the number of things on a die, right? But that doesn't really matter when what they've done is they're not doubling the CPU clock speed. They're not making more powerful CPUs necessarily, not so much. What they're doing is they're sticking more cores on a die. So we end up with, gee, we can't get a faster and faster CPU. Instead, we have to parallelize our code. So massive parallelization is the most sort of feasible way to get at our data quicker and faster and process it better. So do you need to go NoSQL? Do you need to go big data? Do you need one of these other types of databases? Maybe not. If your data is pretty tabular, if it fits cleanly in the relational model and what you're doing with it is really sort of a set problem, if you aren't having scalability issues, if you don't have a large, multi-terabyte data set, or if your data set and problem doesn't really lend itself to massive parallelization, then you can probably stick with your Rdbms for now. And you're probably not, at this webinar anyway. But you may still want to sort of pay attention to this, because you may have this problem later as we're getting more data, more users. We're developing different types of business models that have more parallelization and what have you in them, and higher performance requirements. Maybe you don't have it now, but maybe you will. So this is sort of just a baseline example of a RDBMS example. I took this from a different presentation, so that's why it says JPA. So RDBMS example, so we've got table 1, table 2, table 3, person and person ID, company ID, and then a set of phone numbers linked to that person, who happens to be me. One thing that you have to really separate when you're deciding what types of databases that you're going to use, and it's really something you should have been doing in the RDBMS, in the pure RDBMS era. It's a continuation of a problem companies have been struggling with. There's a tendency at many companies to try and develop, in a RDBMS, a holy schema, the one schema that will fit all uses of data for all time and store everything. And that really doesn't work very well. When you're doing reporting or some sort of analytical processing, you need a different view of the data than when you're doing operational systems. So you've got your website or you've got your inventory system or whatever that needs to just read and write rows really quickly in an RDBMS. One type of database is unlikely to be well suited for all of your problems. So when we're doing search or we're doing a recommendation engine, we need a different sort of data structure than when we're doing a simple lookup or a simple, write one value kind of thing. The system doing long-running reports and generating charts and graphs and statistics is your analytical system. The system doing short and sweet, lightweight transactions is your operational system. So the thing behind your website tends to be your operational system. The thing that your accountants and all those people are using tends to be an analytical system. There's obviously some blurring of the lines between each, but you need to think about those different types of systems and think about your data use when you're deciding what database. So what other types of databases in addition to a relational database are there? So one type of data store is key value stores, and we have examples, Couchbase 1.8, Cassandra. We also have the distributed caches, which are sort of going through a rebranding stage where they're sort of being rebranded as NoSQL. They already sort of existed. We already had these distributed caches. We had things like Terracotta, Gemfire, JBoss Cache, which is now Infinispan, and so on and so forth, Coherence. And now these are going to sort of be rebranded. Before they're called distributed caches, now they'll probably be called in-memory key value stores. These are lookup by constant time in general. So, I mean, this is sort of a giant map, more or less. These are good, excuse me, good for right now style things like stock quotes. These are usually combined with an index for search, but the structure isn't inherently indexed by anything but basically the primary key, anything but the key. So key lookups really quick. Other things, we need some sort of index. A lot of these tend to integrate Lucene, which is an indexing software from Apache. Generally works well with MapReduce. This is extremely scalable. It's also easy to partition. We also have column family or big table. Many key value stores actually also support column families such as Cassandra. Some we design this way. The idea here is that keys and values become composite. Probably the best way to think of this is like a hash map with a multi-dimensional array, so each column is a row of data. This is MapReduce friendly. A good example of this, use with this would be a stock quote with time ranges. So if we're getting the stock quote every 30 seconds or something like that. So this is an HBase example with that same data set. So we've got me, company, and what have you. Notice this is a big table type structure. So it's each row is not necessarily distinct outside of its primary key and the differentiating column or columns. The next type of database we have are document databases. A lot of developers think these are quote unquote the holy grail of NoSQL databases. And the reason for that is they fit really well with modern object-oriented applications, or especially well with AJAX applications, where we're already sort of creating these JSON documents from the front end and then writing them to the back end. We can perhaps eliminate some of the steps of processing. So we're already creating a JSON document. We do whatever processing for security purposes or whatever, and then we might be able to write that directly into our underlying document database schema. So the next version of Couchbase that's still in beta is Couchbase 2.0, and it will support, and it is a document database. An interesting way to look at this that I got when I was interviewing some folks from Couchbase was that one way to think of this is a key value store that actually understands its values. So it can actually inspect and index and what have you the underlying pieces of the values. It's not as MapReduce friendly. Most of these do have some sort of MapReduce framework, but it's not like it's not as MapReduce friendly as a key value store, a column family. Larger data sets do require indexes. It's very clearly fit for REST services, operational store, that sort of thing. And this is an example of that data set here with a JSON document. So usually most of these store JSON JavaScript object notation, sort of that JavaScript format. So here you see my first name, last name, et cetera, et cetera. You see that phone, I've got basically an array of phone numbers. I don't have some separate table somewhere. A lot of folks get hung up on the idea of transactions as the only way to provide consistency, as that's the way you do it in a relational database. However, I can write this document consistently all at once. In a relational database, I'd have the phone number in a separate table, for instance, and I would have to write that in a separate write. This is all one write, one document in most in a document database. The final database that is sort of one of the more popular NoSQL database structures is a graph database. Now these don't fit cleanly into what you're thinking of when you think of NoSQL. You're thinking of this massive scale and what have you. But these are less about the volume of data, or even the volume of, or even the amount of parallelism, the number of users, and it's more about data complexity. Flying in the face, many of these are transactional. Often the transactions are more correct for these data types than those offered by a relational database. And you're like, okay, how can that be? Well, when you think about the default, so most of the time you don't run a relational database in read serialized commit level. If you didn't set a commit option, you don't know what that means, you're probably running in read committed. That's the default for, say, Oracle and Postgres and MySQL and whatever. That read committed does not handle row inserts. So if you were to get a count on a table from a transaction, and then you were to get the count later in a transaction after somebody inserted a row, you'd get two different values. Well, that violates sort of your consistency and what have you. When we're doing graph databases, because the way we store things and what have you, a lot of times these are more transactionally correct than what a relational database offers, because we're doing the transaction on the data elements and what have you, and we don't have this table kind of structure. Friend of a friend and direct path operations are easy. This is very complicated and inefficient in a relational database system. These are usually paired with an index for search. And this is sort of a graphical explanation. Here we've got a relational database system with 3 tables, and there's interrelationships between the data. Here we've got a graph database. So you notice there's sort of it's sort of a similar thing, except there's no table. I write an element here, I write an element here, I write an element here, and what have you, and I relate them. So that's sort of the shape of things. An example of this that sort of shows what I can do that I can't do necessarily as efficiently in other types of databases is here you see me, you see my relationship with the company. You see I have multiple relationships with the company. You see that, and these can be sort of ad hoc, which is kind of nice because you wouldn't really want to have a table, you know, founders when I'm the only founder kind of thing. You have where the company is located. You notice that we have 2 offices, so we're located in 2 different places. The company has a phone. It's also associated with me and what have you. So we have extra relationships and details here in graph databases. So all of these discussions usually are like get wrapped into a discussion about Hadoop. Hadoop is sort of not just like some NoSQL database or the answer to all big data problems or what have you. It's more of a software framework or a project. So a lot of times when people say Hadoop, they're just talking about the MapReduce framework, which is an algorithm, a querying algorithm would be a very simplistic answer to what that is. Sometimes they're talking about the Apache Software Foundation's project called Hadoop, which contains a lot of different projects. Pig is a query language. Hive is basically the manager, what have you. HCatalog for interoperability. HBase is a big table database built on this. HDFS is a sort of RAID over the internet would be the best way to think of it. It's actually kind of a clustered file system. So Hadoop itself refers to different things. It's not just some NoSQL database or what have you. It is a series of things, and it's a pretty complicated set of software to understand. Another movement to sort of understand in this NoSQL space is that there's sort of a convergence of file systems and databases. So Hadoop HDFS is a distributed file system. So is Gluster, Ceph, GFS, etc. And these are used by Linux or what have you for distributed file systems. Hadoop can also use Ceph or Gluster in place of HDFS. So when we're talking about storing this big data structure or what have you, there's sort of now a mishmash between what is file system and what is database and what is MapReduce and what have you. Other derivatives. So there are other types of NoSQL database or whatever. Most of these are either legacy or derived from other types of databases. You know, it's key value store, column family with a twist kind of thing. One is a triple store. Apache Gen is an example of that. The other would be an object-oriented database system. This is sort of a paradigm that we all experimented with and never really took off for various technical reasons and marketing reasons and what have you. The most famous one of those is InterSystems Cache. There's an accent there, but I didn't have the keyboard for that. But object-oriented database systems would be another sort of alternative database that's not necessarily always considered in the NoSQL movement, but it's sort of a legacy type. There are things that you need to consider when picking a database and other things that you need to consider. You need to consider the type of persistence. Is it in memory and then asynchronously to disk or synchronously to disk, or how is that working? Replication. Do we have replicas of the database in memory in multiple locations? And that relates to sort of DR as well as disaster recovery as well as high availability and all that kind of stuff. Availability itself is, okay, if a node crashes, if 2 node crashes or whatever, what's your expectation of your application staying online? Transactions, and less specifically than transactions, consistency. How consistent do you need the data really? Do you need it absolutely consistent right now, this millisecond? Do you need it consistent within a second? You know, does it need to be consistent by the end of the day? Whatever. So the different types of consistency, which is sort of this absolute transactional consistency, eventual consistency, and what have you. Locality. So some of these NoSQL databases also know how to do a read next to me. So if you're getting several pieces of data, it knows that on a particular node, that the data that you're looking up and the data you're about to look up are right next to each other, and it can do sort of an optimized sort of read. Language, what languages does it support? Does it support JavaScript? Is it a JavaScript-based database? Does it support Java? Does it support C? You know, whatever. And then there's some resources that you might want to look up, which one is this Wikipedia article of comparison of structured storage software that's pretty good. And then another one is 7 databases in 7 weeks. So the bottom line is a relational database may not scale to your needs. It also may not fit your data structure. If you're trying too hard, one way I put it is if you're using more than one outer join, you probably don't have a relational algebra problem. Your data may not map efficiently to tables. Your key value store is a data by key. It's fast, scalable. It can't handle complex data because it's basically sort of a map, basically a big map. A column family or big table is fast, scalable, denormalized. It's good for MapReduce, good for series, not efficient for incredibly complex data. You can't really capture relationships in between the different data items very well. Document database is good for operational system. It's probably not your analytical system. It's moderately scalable, and it matches the OO paradigm pretty well, or very well. Graph databases are good for complex data. They're usually transactional, and they're generally less scalable than the other types. And then finally, file systems and databases are actually converging. So now we'll open it for questions. Thank you guys. This has sort of just been a brief overview of the landscape. Happy to answer questions on any particular type of NoSQL database or use cases or what have you, or any questions at all.
Hey everyone, this is Baxter. If you have a question, just use your GoToWebinar panel, type it in, and we'll address it in the moment. So go ahead. Let's see. We have one question. Andrew, what would you recommend for analytics?
So we're still sort of at an early stage for, if you're looking at like the BI type stuff or what have you, we're still sort of at an early stage of that, and they're starting to integrate NoSQL databases into those more, BI type things. If you're just doing sort of more basic reporting, most of your sort of traditional reporting engines like Jasper Reports or what have you have already integrated various NoSQL plugins, in particular Hadoop and what have you. I think also you'll notice that like Microsoft with their BI stuff, I know they've announced that they're going to be supporting and increasing their support for Hadoop and what have you. So it's a little early on some of the analytics traditional BI products, but that's sort of what you're going to next year. Last year was about, hey, what's this NoSQL stuff? This next year is really going to be about, wow, this BI thing now is like master of big data and what have you.
Great, thanks. We have one question. Does it make sense to implement using Scala Akka instead of Java Spring?
So it really doesn't matter too much as far as, I mean, this is your database. So as far as, if you like Scala and you like, in particular, you like the functional programming paradigm or what have you, it's sort of an orthogonal decision to your database structure. So, I'd say it doesn't really matter incredibly which language.
Okay.
And increasingly you're seeing the Scala and Akka stuff announce support for various NoSQL databases. um, integrated with it.
Okay, that's great. We have a couple of questions about Couchbase, and I'm going to punt those until Dipti's presentation because her presentation will probably cover a lot of those questions that we have. I do have one NoSQL question. Does NoSQL make sense for use cases with lots of write but only the occasional reads?
So it can, and it has to do with sort of distribution of the rights. So it can. It does sort of depend, but it can, and it's really okay if we're able to distribute those rights to more nodes, we can probably get a higher throughput. In some cases, you may even go more radical and do more. A lot of folks have been doing some interesting things with some of the Hadoop stuff just because they're trying to get the data out there, but they don't need to really make any sense of it until later in the process. But in general, yeah, NoSQL databases can make sense for that use case. I wouldn't go and use, say, a in-memory key value store for them because, gee, what am I wasting all this memory if, you know, the main reasons for read optimization, or maybe it's a way to increase my buffering to the disk or whatever, but it's still a buffer and what have you. So I probably wouldn't use particular types of things in that structure. But yeah, it would depend on your data structure, but in general, yes, it can. We're just accomplishing higher throughput and what have you through the same sort of stuff. We're just not using the things that would make read optimizations better or querying.
Great, thanks, Andrew. At this time, we'll have to pull up and move it over to Dipti. There are some questions about document databases in Couchbase, and they should be addressed in Dipti's presentation. But if not, we'll pull up at the end there and address the remaining questions. So thank you very much, Andrew, for your presentation. That was great. And at this time, let's hand it over to Dipti.
Hello, everyone. This is Dipti Borkar. I'm the Director of Product Management at Couchbase. At Couchbase, I manage the product roadmap and strategy for Couchbase Server, which is our NoSQL database product. A little bit about me, about my background. I actually come from the relational world. Started off writing core indexing code for DB2, the distributed database, LUW, and then moved from the structured to the unstructured world, moving to MarkLogic and now Couchbase. Couchbase Server is a NoSQL document database. Version 2.0, which will be available soon, is a document database, and it transforms Couchbase from a pure key value store into a document database managing native JSON data. It's really meant for interactive applications, web or mobile applications. And as Andrew mentioned initially, it is more suited towards the operational type of workload rather than an analytics or heavy analytics workload. There are a few core key capabilities of Couchbase Server. It's easily scalable, so you can grow out a cluster without any application changes or downtime, and you can grow or scale down your cluster based on your demand. We have a built-in object level cache, which allows you to give, provides a sub-millisecond latencies for read in as well as write access, and also consistent high throughput across the cluster. In addition, we have capabilities like online upgrades, online backup and restore, online compaction of data, online indexing, which means that you never really have to take your database down for any kind of maintenance operations. And so your application is always on 24 by 365. But most importantly, in version 2.0, we add a flexible data model with native support for JSON data. And with a flexible data model, you no longer have, you're no longer conformed to a schema. So let's take a quick look at an example. As Andy mentioned earlier, document databases allow you the freedom to store data of different kinds, variable sizes, complex data types, and so on. But one of the key advantages of a document database is the ability to make a change to the schema. Typically, in a relational database, to have a schema change, you need to use the alter table statement, which might take a long time to implement. Sometimes it might take weeks to plan out the operation along with the downtime that's needed. So in this example, you might have to create a country table. If you're adding geo data to your application, you need to update each of your tables and make the schema change. But in a document database, on the other hand, a schema change becomes extremely easy because you can update documents, extend them depending on the complexity of your data, and without making any application changes. So you can make these changes, make these application changes, these data structure changes on the fly, and this allows you to rapidly change and update your application, pushing it out in faster cycles. But let's take a look at the underlying architecture of Couchbase. Couchbase server, a cluster of Couchbase server can have as many nodes, from 5 to 25 to 100 nodes, and each node in the cluster is identical. So you have a data manager and a cluster manager that is part of every single node in the Couchbase cluster. Internally, the data manager manages data access, query access, as well as persistence. So it has an object level cache, but it also manages persistence of the data onto disk. And on the other hand, the cluster manager manages the entire cluster, a heartbeat across the clusters. It manages replication as well as rebalance operations to redistribute the data uniformly across the entire cluster. So moving on to some of the basic operations in Couchbase. Let's take a look at a cluster here. So this is a 3-node cluster. In the simple example, we have active data, and you can optionally have replica data as well. You can configure the number of replica sets that you want, up to 3 replicas. And so in this example, we have document 9 that's stored on server 1, and the replica of that document is available on server 3. Couchbase server is strongly consistent at a document level, and so you always read and write from a specific location in the cluster. Now, let's extend this to the application server along with the Couchbase client libraries, which we consider smart clients. So the client itself includes the cluster map, which includes where the shards of Couchbase are located within the cluster. And so when a document comes in, the document gets hashed to a specific shard, 1 of 1024 shards, and the client, the Couchbase client, knows exactly where this document lives. So in this case, the document 5 lives on server 1, and the Couchbase client will directly talk to server 1 and access the document for reads, writes, as well as updates. Now let's see how we can extend this cluster of 3 nodes further by adding 2 additional nodes to the cluster. Multiple servers or multiple nodes can be added to the cluster at the same time, and so you can add 2 to 3 or 5 or 10 nodes to your existing cluster and perform the rebalance operation. And the rebalance operation is what will actually move the data from various nodes to the newly added servers. And so in this case, document 8 and 9 get moved over to server 4, and document 6 gets moved over to server 5. Because of the hash partitioning that's used, the documents are always distributed evenly across the cluster, and so there are no hotspots within the system that you might see when you have range partitioning, for example. And so in this case, your data is now uniformly distributed across. Your load is also uniformly distributed across because of the consistent hashing. Once this operation completes, the cluster map gets updated, and you now know that document 6 lives on server 5 and not on server 3 anymore. And so the Couchbase client will directly access server 5. Now, note here that all these operations that I'm showing, along with the cluster map as well as the direction of the request to a specific server, all this is managed by the Couchbase client for you. And so the application is really completely agnostic of these operations. All the application is doing is saying, I want to perform a read operation or perform a write operation on a key or on a document, and the Couchbase client takes care of the rest. So moving on to failover. So the replicas are used in case of a failover operation. And so while you might have great hardware, in many cases bad things do happen. And in case a server goes down, we have the ability to either use automated failover, and so the cluster detects that a server is down, or manual failover, when an administrator might go in and notice that a server is down and fail over the node, in which case the replica data now gets promoted to active data. And so the subset of the data that was missing because server 3 was down now is available once again to the entire cluster. And so the operations now start getting diverted to the correct servers. In this case, server 4 and server 1 and 2 receive the replica data, which gets moved up, gets promoted to active. So 2.0 is our next version that's coming out very shortly. And there are a lot of great features that are a part of 2.0. We've added native support for JSON along with indexing and querying. So you can create an index over specific JSON attributes and query over those materialized views. In addition to that, we have incremental MapReduce, which allows you to run some real-time analytical jobs on your data set, and as well as cross-data center application, which allows you to move data from one entire cluster to another cluster, maybe in different geos and different data centers, both unidirectionally as well as bidirectionally. So let's take a look at some of these the new features that we have as a part of our upcoming release. Indexing and querying is now distributed across the cluster. And so every node manages an index of the subset of data that it supports. So in this case, server 1 has some active data as well as some replica data for the shards that it is managing. And so the index will be built on the active data as well as optionally on the replica data. And the index building operation is completely online. Once these indexes are built, a query can then be served out of any node in the server. And so in this case, application server 2 issues a query. The client randomly picks a server from the cluster. And so in this case, a cluster of 3 nodes, server 2 gets randomly picked, and it will perform the scatter-gather operation across the entire cluster. So the request comes in, the server 2 will send out a request to all the other nodes in the cluster and get results back, which it would then aggregate and send back to the application server. You can define primary indexes, secondary indexes. You can have complex maps of functions. We also have built-in reduce functions for fast aggregates. And so aggregates like count, sum, and so on are actually stored with the index. And so they are pre-computed, which makes it very, very fast to access aggregates across your entire data set. You can also have define custom reduces if your application requires it. The next feature that I want to talk about is cross-data center replication, which we call XDCR. And XDCR allows you to replicate data from one entire cluster to another cluster. So let's say that we have a New York data center, and we're expanding our business, or we have, turns out we have a lot more users on the West Coast, and we want to start off a West Coast data center. And now we want to have a master replication setup, or a unidirectional replication setup between the two, where data from one cluster gets automatically replicated to another cluster. And so it's extremely easy to set this up. You can point any node in one cluster to any node in the other cluster. XDCR will automatically detect the topology of both the clusters on the two sides and set up replication streams. And so by default, we have 32 replication streams that come off per node in the cluster. And I've simplified this chart where I show one server talking to the other server, but really each server is talking to every other server on the other side, depending on where the shard or where the document lives on. And so replication happens on a per shard basis, and by default we have 1024 shards in the system. And so as active data gets written into the cluster, into the source cluster, it gets persisted to disk. And as it gets persisted to disk, it also starts getting shipped over to the remote cluster in memory, and eventually also will get persisted to disk on the other side. And so in this example, we see unidirectional replication, but you can set up bidirectional replication by simply pointing the remote cluster, in this case the San Francisco data center, to the New York data center, and you get bidirectional replication with the ability to perform reads and writes on both sides. And so you have a master-master or an active-active replication setup. We do have conflict detection and resolution available, and so the system end-to-end will pick the same winner across the two clusters. And so this is eventually consistent. And so while data access within a cluster, within a single cluster, is strongly consistent at a document level, XDCR is eventually consistent across data centers across the two sides. We also have full text search integration with Elasticsearch, which actually uses cross data center replication at the back. And so the adapter, the Couchbase Elasticsearch adapter, will simulate a cluster, and XDCR pushes mutations from the Couchbase cluster to the adapter, and then the adapter will push out all the mutations to Elasticsearch, which is a leucine, a distributed leucine index, which is also a clustered solution. The adapter is completely cluster aware, like all our features. XDCR is cluster aware, and so you can resize your clusters at both sides, and it will automatically take care of any topology changes. This is just a quick view of our UI, and so here you see that you can very easily add servers, rebalance your data, fail over a node or remove nodes, and also define indexes, which are using views, create XDCR applications, and get more statistics about your system. And so the monitoring is built into our admin console. And here you see that there's hundreds of metrics that you can look into to get a view of what exactly is happening across the cluster, and even drill down to individual nodes within the cluster. All these are also available as REST APIs for integration with your other monitoring tools. Before we close out the webinar, I do want to talk about some of the use cases for document databases, particularly the data-driven use cases and the performance-driven use cases. And so on the data-driven use case side, we, in general, document databases support unlimited data growth. And so you can add more nodes as you go, as the need to store more data increases. Data can be non-homogeneous, and so you can very easily represent complex objects, variable length documents. Sparse data is another well-suited type of data to store in a document database. But we're seeing a lot more of the third-party or user-defined structures. If you are streaming in information like a Twitter feed or a Facebook feed, you may not have control over the data structure or the schema. And so a document database gives you the flexibility to store information where you may not have control over the data, and also the data structures or the schema might change constantly over time. On the performance-driven use case side, if low latency matters to you, particularly at a millisecond level, it is key value access will give you the ability to get access to your data really fast. High throughput is another situation where you might have a growing number of users, and you may not be even able to predict the demand for how many users may use your applications. And we've seen this in case of apps going viral, where within a month you might have millions of users accessing your application or downloading your application. And that's a good problem to have, but you need a database that can grow and scale along with your application. In addition, if you have predominant the document access or workloads with a high mutation rate, so if you have a write-heavy workload, Couchbase actually does pretty well because of the low level of locking that we have as a part of our database. And then finally, here are some examples of applications and use cases where a Couchbase solution or Couchbase plus Elasticsearch solution might work well for you. Content or metadata management solutions. McGraw-Hill is looking into this. We have a lot of users that build social applications, social networking or social gaming applications. Ad targeting is an extremely performance-driven use case where low latency matters quite a bit. And we have for object-driven use cases like user profile stores, session stores, where you might store customer information or user data, and that's a good use for key value access to your data as well. And then finally, a high availability caching, Orbit uses Couchbase as their caching tier and replacing caching, entire caching tier with Couchbase clusters at the back. And then another good application would be chat or messaging platform where you need quick access to individual documents. So with that, I'd like to open it up for questions. I know we're a tad bit over the time, but I'll be happy to take a few questions at this time. Let me just take a look at some of the questions that we have here. A question about document modeling. When would you move parts of a JSON document into a separate related document? So that's a good question. In general, what we see is for use cases like user profile stores or session stores, you might store an entire object as one entity in a single document. However, if you have parts of the documents that might grow that might expand over time. For example, if you have a blog application and you have an extremely popular blog, or in general the blog is extremely active and you have a lot of comments that keep coming in and replies to posts, you might want to store the comments in a separate document and link it to using the document IDs, which is a document ID is like a primary key. And so that's one of the use cases where you might need to separate out the documents to be able to have more control over the size of each document, so that you're not always transferring large documents together, and you have more control over the growth of the comments. What is the best approach to convince my managers to use a NoSQL database? Well, as Andrew mentioned earlier, and as I mentioned with some of the use cases, it really depends on your application requirements. A relational database might be a good fit if your data is extremely well structured, and so perhaps for an order management system too, I wouldn't recommend moving to a NoSQL database. However, if you have varying data structures and sparse data, as I mentioned earlier, hierarchical data or complex structures, and your relational database is not able to keep up with either the demand to store data, or where we've seen most trouble with is write throughput. You're not able to scale your write throughput. Might be good to these may be the reasons why you convince your manager to use a NoSQL database, whether it's a key value store, a document database, or a graph database. How do I calculate the number of nodes in my cluster? That's a good question. Sizing is, particularly for document databases and the more complex kind of databases, is more of an art. But we do have some techniques and the guidance on sizing, and we can point you offline to some of the best practices, which will give you an idea of how many nodes you need in your cluster. In general, we like to have the working set of your data in memory, which means that if you have 40% of your working set of the total data set is active and heavily used, then to get the best performance with the sub-millisecond latencies, we recommend that your working set sit in memory, and so you can use that as one of the metrics for sizing. Of course, if you have write-heavy workloads, you might need more I/O or disk capacity and throughput and so on. And the last question that I'm going to take here is related with Couchbase Server 2.0. The question is, when we persist a document, are we able to immediately fetch the persisted document in a query? This depends on you have the option. By default, the indexes are eventually indexed, which means that your queries are eventually consistent. And so from a document access perspective, your documents are always strongly consistent. So if you read, write, update a single document, you have immediate access to it. It gets asynchronously persisted to disk and then gets indexed. But you do have the option of waiting for it to get indexed. So we have durability constraints where you can use the option of persisting it to disk, and then you get a strongly consistent query result. All right, with that, I would like to say thank you very much. Do feel free to contact us at these email addresses. We'll try to get back to questions that we haven't been able to answer as a part of this webinar. And we hope that this webinar has been useful to you as you navigate your way through NoSQL. Thank you very much. Bye-bye.